All right, absolute value equations and inequalities. These are special types of equations and inequalities that involve the absolute value symbol and need to be treated in a special way. So for instance, the absolute value of x equals 3. What are possible values for x in this instance? If I take the absolute value of a number, what does it do to the number? Makes it positive, or if it is positive already, it doesn't change it, right? Because it's telling you what? The distance the number is from the origin, right? So if I take the absolute value of a number and I get 3, what are possible solutions?
3 and negative 3.
Yep. Negative 3 and 3, right? I just essentially just take a negative. I take the positive and I throw a negative sign, and I get both of them, right? On the other hand, what if I had absolute value of x is less than 3? What would possible solutions to that one be? That's saying that if the absolute value of x is less than 3, absolute value of x is the distance of x from the origin. So if the distance from the origin of x is less than 3, what does that mean? What are all the numbers that could possibly, if we're thinking about the number line here, what are all the numbers that are less than 3 from the origin?
Negative 2.
What about like negative 2.5 and positive 2.99999? So what should I do there? X has to be what? Between what and what?
2.999.
X is greater than negative 3, but less than 3.
Between negative 3 and 3, right? Just use the open, just use a less than or greater than. It doesn't include 3 itself, but everything up to 3. Everything including 2.9999999 forever, right? So x has to be less than 3 and x has to be greater than negative 3. So we just say, we take the less than 3, put it in there, and throw in an and. It's always going to be the word and because it's between. It's an intersection, right? And x is greater than negative 3, which we could also just write as in this way too, right? But if we sort of forget, we can always know that if it's an inequality like this, we can write we can break it apart into 2 separate statements. X is less than 3 and x is greater than negative 3. If it's less than, we always use the word and. And then for the first one, we just keep it the same, right? We just take the less than 3, we keep that, and we just take off the absolute value sign. And for the second one, all we have to do is switch the direction of the sign, change the sign of the number, right? And that's going to be the same process we would use if it's x is greater than 3, except we're going to use a different word, right? Now we're saying I want all the numbers that are more than 3 from the origin. So that would be what? All the numbers that are more than 3 from the origin. That would be numbers that are to the right of 3 and to the left of negative 3, right? If we're thinking about the number line again. So how could I write that?
It's a union.
It is a union, so what word should we use? X is greater than 3, or what should the other statement be? X is less than negative 3. So once again, this part is the same process. We take the sign and the number, we keep it the same for the first one and just get rid of the absolute value sign. For the second one, we change the direction of the sign, change the number, and that always works, right? We can't combine this into one statement, though, so we're going to leave it like that, but we are going to write both of these in interval notation. So for this one, let's say this one right here first. What would be the interval notation for negative 3 to 3? Interval notation for that.
Negative 3 and 3.
And these need to both be parentheses, right?
Yeah.
Because it's open, not including 3. Now what about this one right here on the left? Let's look at the x is greater than 3, or the x is less than negative 3 part. How would I write that? All the numbers to the left of negative 3 all the way out to negative infinity.
Open, negative infinity, comma, negative 3, close.
Closed or open? It's less than, right? So open, yeah. And the other one's going to be, oh, sorry, I already gave it away. Open, and then 3, and then infinity, right? What symbol do I combine them with? Or as a union, yes. Okay, so we need to be able to write all of our answers now in either inequality notation or interval notation. And I'm going to have you be going both ways on the homework tonight. I'm going to give you some intervals that I want you to write using inequality notation and vice versa. And the vice versa part is all of your answers you need to convert into interval notation once you're done solving the inequality. So that's how we deal with absolute value equations and inequalities. And so that same idea holds even if what's on the inside of the absolute value is more than just x. It can be any expression on the inside of that absolute value sign. We're still going to solve it the same exact way by breaking it apart into two separate statements. So I'm going to give you some examples of that right now, and I want you to go ahead and solve these. So if I have like absolute value of 3x minus 5 is equal to 7, for instance. Or if I have like absolute value of 2x minus 3 over 4 is less than or equal to 2. All right? Want to go ahead and solve both of those for me right now using the same strategy, except the only difference is you have stuff on the inside of the absolute value sign, but the same strategy still holds. All right, so the first thing we're going to do here with the first one, absolute value of 3x minus 5 equals 7, is we're going to break it apart into two separate statements. We're going to say, well, that means 3x minus 5, whatever that is, has to either be equal to 7 or it has to be equal to negative 7. That's the only way that that would be possible, right? And then we can just go ahead and solve each of these separately. So we'll get 3x has to be equal to 12, so x could equal 4. Otherwise, 3x has to equal negative 2, which means x could equal negative 2/3. So either x equals 4 or x equals negative 2/3, right? And anytime, notice, and we've always done this without actually thinking about it, we always use the word or when we combine two individual solutions, right? Because that is a union, right? We want either the x equals 4 or the x equals negative 2/3. We want to combine that into a single set that includes both of those numbers. Those are all the numbers that are solutions to that inequality. The one down here, it's an inequality, so in addition to changing the sign of the number when we break it apart into two statements, we also have to write it as two separate statements. Sorry, we also have to change the direction of the inequality sign. So we'll write 2x minus 3 over 4 is going to be less than or equal to 2. I'm going to use the word and or? And 2x minus 3 over 4 is greater than or equal to negative 2. So we'll get, I'm gonna do two steps at once here. I'm going to multiply everything by 4 and then add the 3. So we'll get 4 times 2 is 8, plus 3 is 11. So we'll end up getting x is less than or equal to 11/2. And over here, I'm going to multiply by 4 to give me negative 8, and then add the 3 to give me negative 5. And so we'll get x is greater than or equal to negative 5/2. All right. So x is less than or equal to 11/2, and x is greater than or equal to negative 5/2. So I would write that in interval notation as what?
Bracket negative 5/2, comma 11/2, closed.
Yep. And the interval notation version is a lot easier to graph on the number line, right? It's a lot quicker to graph on the number line, because you have to look at the x is less than or equal to 11/2 and the x is greater than or equal to 5/2 and realize that, oh, that just means everything between negative 5/2 and 11/2, right? So that's how we deal with absolute value inequalities and equations. Now, the last topic of the day, quadratic, right, and other inequalities. Which you probably haven't really tackled before. So this will be sort of a new topic. We're starting our first really genuinely new topic of the class so far. So a quadratic inequality, as you might imagine, is just an inequality that involves a quadratic function. Pretty straightforward, right? So for instance, if I had like x squared, let's say minus 2x is greater than, God, I wish my greater than signs looked better, is greater than, still bad, but whatever. Yeah, that's too big. 35. Okay, is greater than 35. So you're looking at that going, well, that's a totally different situation, because normally when I solve quadratics, I don't solve them like I solve linear equations by isolating the variable. So in the case of an inequality that is not a linear inequality, we can't solve it by just isolating the variable. We need a new strategy. We can't isolate the variable in this case. We are also, as in the past though, going to use the same strategies we've used in the past. We're either going to use factoring or we're going to use quadratic formula. And this is the way we're going to handle it. First thing we're going to do in the case of any quadratic inequality or any inequality that is not linear is we're going to get everything on one side. Now, graphically, what does this represent? We're saying that x squared minus 2x minus 35 is greater than 0. We're saying this quadratic function, where is that greater than 0? On the graph, what are we talking about there? We know this graph is going to be a parabola. Let's go ahead and actually do that really quickly. How would I graph this equation? I would factor it, right? I need to know like the x-intercepts first, right? So how is this going to factor?
X minus 7. No, I'm sorry. Yeah, x
Yep.
minus 7, x plus 5.
So my two x-intercepts are going to be what?
Negative 7 and 5.
So other way around, right?
Yeah.
Negative 5 and 7. So let's say if I go ahead and graph this, negative 5 is right there, 7 is right here. Is this going to open up or down? Up, because A is positive, right? And so I don't actually really, it doesn't really matter where the y-intercept or the parabola are in the case of this problem. Sorry, or the vertex, I should say, are in this problem. But we know it generally looks like that, right? That's the graph of the function. So let me ask you the question again. When we're saying x squared minus 2x minus 35 is greater than 0, what is the graphical significance of that statement? We're saying, when is the what greater than 0? That's the what of the function. That is the function, right? And that gives me the what of the function. If I plug in x to this right here, that's going to spit out the what of the function at that value of x. The y value, right? So we're saying, where is the y value of the function greater than 0? Graphically, what does that mean? Where is the function above the x-axis? And so if you look at the graph, you can say, well, it's above the x-axis here, and it's above the x-axis over here, right? And so if you know what the graph looks like, and you know where the x-intercepts are, and you know where it's below the x-axis and where it's above, well, that sort of solves the problem right there. Where is the y value of the function greater than 0? So, it's the question, where is the y value greater than 0, which means above x-axis, right? So we want to find all the intervals where the where the function is above the x-axis, and so that would be to the left of negative 5 and to the right of 7, right? So how could I write that as I can just go ahead and write my solution right here, can't I? What's the left part of the solution going to be, the less than negative 5 part in interval notation?
Infinity and -5.
And open, right? And then the right side is going to be, what's the intercept here? This is negative 5 and this is 7, right?
So A 7, comma, infinity.
And what word should I use to put these together? Union or intersection? Or I mean symbol, I should say. Because I want all the stuff to the left and all the stuff to the right. I want to take those two sets and combine them into one set. So I have to use the union for that one. So it's a matter of, in the case of a quadratic, get it all on one side to make it, to get it into general form, and then figure out where its x-intercepts are. And then depending on whether it opens up or down, you can tell where it's above the x-axis and where it's below the x-axis. If it's greater than, it means I want to find the set of all the numbers that make this above the x-axis, right? And if it was less than, it would be the opposite. We would just put the numbers between negative 5 and 7, right? So we can use the graph to understand it's best to use the graph to really understand nonlinear inequalities, right? Now, let's say, on the other hand, you have one that's not factorable, which is more often than not the case, as we know. We're going to have to use quadratic formula. And so we're going to want to use what we know about this. And we're going to actually not even use the graph for this next one. If I have, like, let's say 2x squared is less than or equal, is less than or equal to 3x plus 1. And hopefully this isn't factorable. And so we have a quadratic. First thing we're going to do, if it's quadratic or if it's anything that's not linear and not an absolute value inequality, we're going to immediately put everything on one side. So we'll get 2x squared minus 3x minus 1 is less than or equal to 0. Now, first of all, we ask ourselves the question, is that factorable? So if we weren't sure, we would go ahead and do, okay, fishbowl. We're looking for a difference of 3, which doesn't exist, right? I can't make a difference of 3 from the inner to the outer product there, so it's not factorable. So we're going to use quadratic formula to find the x-intercepts of this parabola, right? So we will do negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And so I'm just going to go ahead, 9. 4 times 2 times 1 is just, that's positive 8, so 9 and 8 is 17. So square root of 17 over 4. And what I'm going to do is I'm going to go ahead and, because I can't do much with this sort of like, this irrational number here, so I'm going to take my calculator and find decimal approximations for both those solutions. Let's go ahead and do that while I talk into the thing. All right, so we want to use test values. What we've done here is we found that the critical values, what we're going to start calling the critical values, the x-intercepts of this function are 1.781 and 0.281. We've made what we're going to call a sign chart here for the function, right? And we're trying to figure out where is the function above the x-axis, this function right here, and where is it below the x-axis? It can only go from above the x-axis to below the x-axis, or vice versa, when it actually crosses the x-axis, because it's what we call a continuous function, right? So right here, if it's going to actually change sign, if it's going to go from above to below the x-axis, it actually has to hit the x-axis, which happens here, and it happens here. So we're going to find test values in each of these 3 intervals, which is what these 2 x-intercepts break the number line into, and we're going to test those by plugging them into this function right here to see if a value over here makes this less than 0 or greater than 0. A value between these two makes it less than or greater than 0. And a value over here makes this less than or greater than 0, right? This is either going to confirm or unconfirm this hypothesis right here, that it's above or below the x-axis. So I'm going to use the numbers -1, 0, and 2 as test values. If I plug in -1 to this expression, and it gives me a negative value, that means that this statement is true, and that this entire interval, if anything over here is less than or equal to 0, then everything over here has to be below the x-axis. I'll do the same thing with 0, which is between these 2 values. I'll plug it into here and see if it's less than or equal to 0 or greater than or equal to 0. And I'll do the same with 2. I'll plug 2 in and see if it makes this less than or equal to 0 or greater than or equal to 0. And by testing each of these intervals, I can tell where the function is above the x-axis and where it is below, and that will give me my intervals. So when I plug in -1 into this function right here, I get +4, which means that all the values to the left of -2.81 for x are going to give y values that are greater than 0, which means that the function is above the x-axis in this interval, which doesn't meet this condition. So this interval is not going to be part of the solution set. If I plug in 0, I get -1. If I plug 0 into this, I'm going to get -1. Which is negative, so that means that all of the y values between x equals -2.81 and x equals 1.781 must all be negative, meaning it's below the x-axis over an entire interval, which means this will satisfy this particular function. And then lastly, we'll plug in 2. And if we plug in 2, we get +1, so that means that all of the values to the right of all of the y values to the right of x equals 1.781 for this function are positive, meaning the function is above the x-axis, and this is not true. It's not less than or equal to 0, the y value here. And so the only, looking at the sign chart here, the only interval over which this is true is this interval right here, -2.81 to 1.781. That's going to be a closed interval because we're talking about less than or equal to here. So it's going to be -2.81 sorry, 0.281, sorry. As soon as I can find my eraser, we will, well, there we go. Of course. Okay, let's try this one more time. All right, so we're going from negative 2.81 or 0.281 to 1.781, and that's closed. All right, so that is how we use a sign chart if we had no knowledge of what the graph looked like whatsoever, right? Which might be the case for some non-quadratic ones, which you might see on the homework. All right, and so we can use the graph of whatever function we have in the inequality here to figure out where this is true by putting everything on one side and then figuring out where it's above or below the x-axis by identifying the x-intercepts and then just looking at the graph. Or we can make a sign chart which accomplishes the same thing and use test values, right? All right, so let's go ahead. I'm going to have you do an example that's actually not quadratic on the next slide. Go ahead, and you're not going to be able to solve this one by factoring, but I'm going to have you use your calculator actually and figure out where is the function x cubed minus 2x greater than 9, let's say. Okay, x cubed minus 2x greater than 9. Where is that true? This is a nonlinear, it's actually a cubic function. It's not a quadratic function, so you can't solve by factoring or using quadratic formula. And so you're going to have to go ahead and use your calculator. What I would do is graph, first get everything on one side, take that function that you've gotten all on the left side of the inequality, graph it, all right, see what it looks like, and then identify, you can use your calculator to find the x-intercepts since you don't have any other way of finding the x-intercepts, right, where the function is equal to 0, and then use those to build an interval over which the function is either above or below the x-axis depending on what the inequality tells you. All right? We'll come right back. So, the strategy I told you to use is to go ahead and take this inequality, get everything on one side, so I went ahead and I subtracted the 9 from both sides to get this set up right here. And so I want to know where is this function right here, the y value of this function, x cubed minus 2x minus 9, where is that greater than 0? Meaning, where is the function above the x-axis? Over what interval is it above the x-axis? So what I did is I took this function right here, and as I indicated, I graphed it on my TI-84. Zoom standard in this case was a perfect fit for the graph. And then I went ahead and I used my root finder, the second calc 0 function, second calc 0, to determine that the x-intercept here is 2.398. So just a really quick review of using the root finder on your calculator. If you have a TI-84, you do second calc 0, right? And it's going to ask you for a left bound, so you take the cursor and put it anywhere over here to the left of the x-intercept you're trying to look for, and you hit enter. Then it's going to ask for a right bound, so you take the cursor and put it anywhere on this side, up here, down here, as long as it's to the left of this x-intercept, and hit enter. And then it asks you for a guess, so if you want to, you can scroll the function or the cursor as close to the x-intercept as possible to make it the calculator's job easier, and click enter for a third time. And in the lower left-hand corner, it's going to tell you that x at this particular point is 2.398, and that's your x-intercept for this function here. That's where this equals 0, right? And so this function right here equals 0 at this point, which means it went from negative to positive at this point, right? It was below the x-axis to the left of it and above the x-axis to the right. And so we want to know where this function is above the x-axis, where its y value is greater than 0, and that would be to the right of this point. So how would I write that in interval notation? All the numbers to the right of 2.398, and of course not including 2.398 because this is greater than and not greater than or equal to, right? So how would I write that in interval notation, guys?
Open negative infinity, comma.
Whoops. We're starting with 2.398, right, and going to the right, aren't we? Because it's greater than, not less than.
So
It's okay.
open 2.398, comma, and then infinity, open.
Yep, there we go. So that's it. I mean, if you can either, if it's a quadratic, you should be able to find these zeros using either factoring or quadratic formula, but in this case right here, if it's a non-linear, non-quadratic function, like a cubic in this case, or any other type of function, you're going to use your calculator, get everything on one side, graph it, find the x-intercepts, right, and then look at the graph to figure out where it's above and where it's below the x-axis, and those x-intercepts will break it up in intervals, and you want to pick the intervals where this, whatever condition you have here, either greater than, less than or equal to, or greater than or equal to, is true. Where is it above or below the x-axis? And then write out your intervals as your solution here. And this works for any function, whether it's quadratic, linear, or any otherwise, right? Of course, linear functions, you're still going to use the old method of just isolating the variable because that's the fastest way. But for anything nonlinear, this way of doing it is very useful and very easy. But we should also know if it's a quadratic, let's know how to use a sign chart as well. Or even if it's a non-quadratic function, we should know how to use a sign chart. Because we won't always have a graphing utility, unfortunately. And the sign chart's a great way to go if you don't have a graphing utility and you don't know what the graph of the function looks like, which, believe it or not, will happen occasionally. All right, well, that's it for today. Okay, the following is your homework for tonight. From the same worksheet that you've been working on, I want you to do 1 and 2. In addition to the directions that the worksheet gives you, I think it asks you to tell whether the intervals are closed or open. I want you to also write the intervals in inequality notation. For 61 through 71, so for 61 through 71 odd, I would also like you to write all of your solutions in interval notation. And for number 81, which is a projectile in motion question, which you might be familiar with from Algebra 2, I'll explain it more tomorrow. I want you to take a crack at it first, though. But the formula you'll need to use for number 81 is h is equal to rt minus 16t squared. So if you want to look that up online or whatever tonight, if you're having trouble with it, that's fine. And then tomorrow, if you're still having trouble, we can go over it in class. All right, have a good one.